Okay, hi everybody. So now we're looking at this Napoleon Dynamite one where we want to see, based on the data that we found before, would he be able to throw it over this mountain? So we're assuming that he throws at an angle of 35 degrees, initial velocity of 62.79 meters per second. The base is 3,261.22 meters away, and then the height is about 1,000 meters. So we want to figure out, will he be able to make it over? So what is the maximum height that the football will reach? That's really the first one that we want to look at. So we're looking at, based on these parameters, what's the maximum height? So what we can do is kind of over here set up what we know about the y direction and what we know about the x direction. So for this case, sure, he has to throw it this x direction, this x distance, but there's no guarantee that he'll make it that far. So for right now, all these numbers are kind of worthless because this is what he needs to get to, but it's not necessarily what he will get to. So this right now is unnecessary. We just need to look at the actual parameters of his throw. So in the y direction, we know that he is going to reach some sort of height, which is what we want to find. We know that his y naught is just going to be 0 meters. He's starting throwing from the ground. We know that his v naught is equal to 62.79 meters per second. But what we want to think about before we go any further is that that's not v naught in the y direction. We have this total v naught of this 62.79, but it's not equal to our v naught in our y direction. So what we have to do before we go any further is just a little bit of trig to help us figure out what is v naught y. So if we're looking at this, we can say, well, I want this piece that is opposite of my angle. So I can say, okay, well, v naught y is my opposite, and my hypotenuse is this 67.79. So I really have opposite and hypotenuse, and I have my angle. So I can use sine. I can say that sine of my angle is equal to opposite over my hypotenuse. And then I can solve for v naught y and say 62.79 times sine of 35 is equal to my v naught y. And I can plug that into my calculator. And I get an initial velocity in the y direction of 36.01 meters per second. So that is my v naught y. Alright, and then that's really all that I know right now, or I guess I know in the y direction, my acceleration is equal to negative g. So what we want to do when we're dealing with projectile motion is we can think about splitting it into two pieces. So we can think about it as what's happening in the y direction. So we go up and then come back down. And what's happening in the x direction. So the y direction is really nice because we know something really specific about when we throw stuff up. We know that the velocity at the top in the y direction is just going to be equal to 0 meters per second. This object has to turn around, and in order to turn around, we have to stop. For a really, really brief moment, it has to come to rest, and then it turns around. So in order to do that, we have to stop. So we know that happens at the very top. So actually what we do know, we can come back here and say, well, we also know the velocity at the top is just equal to 0. So that's kind of the last piece of the puzzle that we need. So what we know now is we can say, okay, we have this y equals y naught plus v naught yt plus 1/2 at squared. If we're looking at this equation, we don't so much, or actually we could use this one, but let's use the other one and then we'll go back. But so then with this equation, we're saying, well, we know stuff about the final velocity, we know stuff about the initial velocity, we know the acceleration. We can figure out how much time it takes to reach the top. So we can say vy equals v naught y plus at. So we have that other equation. So we know at the very top, our velocity is 0. We know that v naught y is 36.01. And we know we have acceleration of negative 9.8 times t. 36.01 equals 9.8 times t. So we can say that the time in the air is equal to, or the time in the air to reach the top is 3.67 seconds. Then we can use this y equation and figure out what height is that happening at. We can say y is equal to 0 plus our v naught y was 36.01 times, now we know our time is 3.67 seconds, minus 1/2, 9.8, 3.67 squared. All right, then we can plug that in, and we find that our y is 66.159 meters. Cool. So another way that we could have done that if we wanted to, if we didn't want to find time the way that we did, is we could say, well, we could use this equation and kind of look at the whole entire projectile path. So we can say we started at a height of 0, we ended at a height of 0. So we could use this equation and say 0 equals 0 plus the 36.01 t minus 1/2 at squared. 36.01 t equals 1/2 9.8 t squared. Cancel out a t. Then we'd find that our time, when we solve for that, the time for the full path is just going to be double our time that we found before, so it'll be about 7.34 seconds. Then you would use that information and say, well, it took the full time to be 7.34 seconds. I know that the half the time, the amount of time it took for it to get up is going to equal the amount of time for it takes to get down. So I could divide this time by 2 and say the time at our top is the 3.67 seconds, and then do this process that we did. So instead of, if you didn't want to use this velocity equation, you could have used this position equation twice. All right, so what's the maximum height that we reach? 66.159 meters, which is not good because we need to have a maximum height of 1,000 meters. But so then at what horizontal location x is the football at its maximum height? So we will go over to our x equation. So in our x direction, we know that we want to figure out some position at some time. So we can use our position equation. So in this case, we know the acceleration for x is 0. We can say x naught is 0. Say x equals v naught x times the time that this is happening at. So the time that we care about is the 3.67 seconds that we just solved for. So we want to know at what time, or at what location are we at our maximum height. So we know that the time it takes to get to the top will be the time it takes to get to that x location where we are at the top. So then what we have to do then is just say, well, we need to figure out what v naught x is. So we can do the same process that we did up here and say, in this case, v naught is our adjacent angle. So we can say cosine of 35 is equal to my adjacent v naught x over 62.79. So then v naught x is just equal to 62.79 cosine of 35. So we have a v naught x of 51.43 meters per second. So x equals 51.43 times 3.67. So x equals times 3.67. So that'll only be happening at 188.748 meters from where he threw it. So if we look at this and kind of uncover it, it looks like he's not going to make it over the mountain. It looks like he'll have a highest point of only 66 meters, and that'll be happening 188 meters away from the base of the mountain. So things are not looking good. No. All right, so now we want to figure out what velocity would he have to throw it so that it would just barely make it over the mountains if he throws it at this 35-degree angle. So this one, it's kind of the same exact process that we just followed, except for what we want with our projectile path. Let some space. What we want is a projectile path so that at the very tippy top, we have a height of 1,000 meters, and that's happening at an x position of, what was it, 3,000, 3261.22. All right, so now what we have to do is just kind of work backwards. So we're going to say, let's set up the x equation first because it's a little bit easier. We ended up with that x equation. It's that x equals v naught x times t. In this case, we want to figure out initial velocity. So we can say 3261.22 equals v naught cosine of 35 times t. So we don't know v naught, we don't know time, but that's okay. And then in our y direction, we had that equation that we said y equals y naught plus v naught yt plus 1/2 at squared. We know that we started a height of 0. Yeah, we want to reach a height of 1,000. So 1,000 equals v naught sine of 35 t, and then plus 1/2 at squared, so minus 1/2 9.8 t squared. So now we have two equations and two unknowns. Oh, sorry, this is 4.9. All right, and we can really go about this two ways. We can either plug in for t or plug in for v naught. I think I'm going to plug in for t, because really what I want is v naught. So I'll solve this for t, so we end up with an equation for v naught. So I'll say t is equal to 3261.22 divided by v naught cosine of 35. And I can plug this equation for t into this one down here. So I can say 1,000 v naught sine of 35 times minus 4.9. Then we have t squared, so we have to square this whole quantity. Okay. And now we just have a lot of algebra in front of us. I'm going to pause this and do the algebra and then get back to it. Okay, so that was a lot of algebra. I didn't want to bore you with it. But so once we plugged it in, we can cancel out v naught in this equation, and then we can do out the math for everything. So I did sine 35 times 3261.22 divided by cosine 35. We get this 2283.53. And then squared 3261.22 over cosine 35. So when you have that squared, you get 1585006.8 divided by v naught squared, multiplied 4.9 by this 1585006.8. And then I said 1,000 is just a number, 2283.58 is just a number, so I can subtract the 2283.53 from 1,000. We get negative 1283.53 equals negative this whole quantity. I canceled out the negatives. I have 1283.53 v naught squared is equal to this then. I just kind of brought the v naught squared over, multiplied both sides by v naught squared, then divided both sides by 1283.53. Then we get v naught squared is equal to the square, or v naught squared equals 60509.17. That's what you get when you divide these. And then when we take that square root, we end up with an initial velocity of 245.986 meters per second. So that is how fast he would have had to have thrown it in order to make it over. So 245.98 meters per second. And then I just wanted to give you a chance to kind of think about graphing these. So I don't care too much about the numbers. I just kind of care about the general trends. So what we're looking at is I want to see horizontal velocity versus time and then vertical velocity versus time. So we're looking at horizontal velocity versus time. we know that horizontal velocity is just going to be constant. Nothing is accelerating it, nothing is speeding it up or slowing it down. So the general trend of this horizontal velocity versus time graph is it starts off with some horizontal velocity, and then it maintains that. There's no acceleration to it. For vertical velocity versus time, we know this is a little bit of a different story. It's going to start off with some sort of positive vertical velocity, and then it's going to reach the very top point where it has a velocity of 0 meters per second in that y direction, and then it'll turn around and it has a negative vertical velocity for an equal amount of time. So we know that these are going to be kind of equally spaced out. So with the vertical direction, we know if we kind of trace it out, it starts off with a large positive velocity. That velocity is decreasing at a constant rate, so we have this constant slope, comes to rest, and then it starts increasing its velocity in the negative direction, which we see over here. So it has 0 velocity, and then it gets progressively more and more negative as time goes on. So that was that one, and yeah.